Hi, welcome here. We are graphing linear inequalities in two variables. So this is going to be on our coordinate plane, our xy axis, and we're going to be graphing not just a line, but a region that satisfies the inequality. Before we do that, though, that was really complicated what I just said. That was probably really confusing, and that's okay. We'll unconfuse you. So recall an ordered pair is like your x and y pair. It's a solution to the inequality if the inequality is true when you substitute in x and y and simplify. So that's not too bad, right? We can do that. So does it make it true? If it is a solution. In solutions, we shade. So is 1, 2 a solution? Remember, 1 is your x and 2 is your y because x comes first and y is second. So now let's substitute that into our inequality statement. So the 1 goes in place of x, the 2 goes in place of y. We want to know if when I simplify this, or you can just punch this in your calculator to simplify it, is that actually greater than or equal to 10? Is that true? Yeah, so we get 2 and we get 10, so that's 12. Is 12 greater than or equal to 10? Yes. So yes, 1, 2 is a solution. Now, is that the only solution to that inequality? We want two pairs of numbers that when you plug them in here, you get something bigger than 10. There's actually a ton of solutions, folks. If you kept this one constant, so let's just keep x1. If you kept on increasing your y's, if you made this 4, 5 times 4 is 20. 20 plus 2 is 22. It's going to work. You're going to keep increasing the y's, and that will give you a bunch of other solutions, other points on a graph. If we were to graph it, other points on the graph that work. And same with if you kept this 2 constant, maybe we could even dip down a little bit. In fact, we could. If we increase this to some massive number, we could even decrease this a little bit to make it greater than or equal to 10. So what I'm trying to say here is there are a ton of solutions. There's a ton of coordinate pairs that are true here. This one I think is going to be a solution. So let's try 2 times 6 plus 5 times 1. Is that greater than or equal to 10? You get 12 and 5, that's 17. Yes, you do. Let's try this one. 2 times 0 plus 5 times negative 1. Is that greater than or equal to 10? Nope. This one's not a solution. So that's what I'm trying to help you see here is what actually makes something a solution. If something is true, that point is a solution. What we're going to do today, instead of listing all the points, because you literally would spend the rest of your life trying to list all the solutions, instead we can do this very quickly. We can say all the solutions just with a graph. So we're going to graph, it's 2 steps really. We're going to graph the corresponding equation. We're going to pretend there's an equal sign there instead, in standard form or in slope-intercept form. If you are using standard form, find the x and y intercept. And if you're using slope-intercept form, use the slope and the y-intercept in order to graph it. Now here's one little caveat. So we're going to graph a line. Actually, so this part's pretty important. I'm not going to even say it or read it right now. Let's just kind of that's going to be a part that we're going to come back to. So I'm going to actually graph example 3 first because that's in slope-intercept form, and many of you like slope-intercept form best. So the y-intercept, or b, is -1, and the slope is 2. Remember that means up to right 1, rise over run. So, boom, -1, our y-intercept's right there. We just use that once, that's where we begin, and then we move up to right 1, up to right 1. And then you can reverse your arrows and go down to left 1. That'll keep the points collinear in a line. Boom. So there are my dots. Now here's where we gotta pump the brakes and look back up at what I keyed on to. Now, before we zing this line, we're going to use a dashed line if we have a less than or greater than sign, which is what we have. It's kind of like how typically when we have these symbols, we use open dots. to show a point or a one location. Now for a line where we can't do an open line, that doesn't, we won't be able to see it. But we do a dash line instead to show that those are not solutions to the inequality. Whereas if we have a greater than or equal to or less than or equal to sign, we usually shade, we do shade in that dot. That means we make it a solid line. So I'm not very good at making dashed lines. Some of you might make a solid line and erase parts of it, or it doesn't need to be perfect. It doesn't need to be the straightest thing ever. You just look at like kind of doing a dash through each dot, but making sure you're not connecting the dashes. There we go. So anyway, I just graphed that line. Yeah. Then test a point on either side of the line to determine if it is a solution or not by plugging it into the original inequality. If I graph this line correctly, which I think I did, either this side is the solution or this side is the solution. It's one or the other. This is a line in the sand, and one part is the solution set, and the other part is not the solution set. So if 0, 0 is not on the line, you should test that point. That's the easiest point to test. So I'm going to label this as my TP, my test point, 0, 0. So I'm going to plug in 0 for x and 0 for y. What's sweet again about zeros is simplifying this right side's easy. I mean, I have to do any multiplication here because 2 times 0 I know is 0. So it's just whatever this constant is, it's -1. Now, is this true or not? Is 0 less than -1? Or you could read it as -1 greater than 0. This is false. So the test point is not a solution, it's false. So then shade the other section. So I was testing this point right here, and it's a good thing to actually mark where the point is. I was testing this point on this side of the line. Therefore, I was testing this region. This point is not a solution. Therefore, this region, or this side of the line that it lays on, is not a solution. So that means this is the solution over here. And I don't care how you shade it, doesn't need to be pretty, that's good enough. If it's false, you shade away from the line. Away from line. You might want to add that to your notes. If it's true, you shade towards line. From the point. From TP. Alrighty. So here, folks, if you're into graphing in standard form, you could find the x-axis or x-intercept, excuse me, by what makes when y is gone, when y is 0 or nothing, 0. What does x have to be? X has to be 5. So that means that the x-intercept is 5. 1, 2, 3, 4, 5. Similarly, to find the y-intercept, let's make x become nothing or 0. So when x is 0, what does y have to be? It has to be 2. So the y-intercept is 2. So now you can buzz a line through there. You would make it solid. Now, if that didn't make sense what we just did, many of you are like having this in slope-intercept form. So we would solve for y. So we'd subtract 2x. I'm going to put the x term first, so -2x plus 10. The 10 is positive. And then divide by 5. So in slope-intercept form, we get y is greater than or equal to -2/5 x plus 2. Meaning the y-intercept is 2, and we go down to right 5. Hey, when we do that, we get that point. Hey, see, there's a few ways to do this algebra stuff. That's pretty sweet. I'm going to go up 2 and left 5, and that gives me this dot. So that's the weakness to finding the x and y intercepts. Then you gotta, well, I guess you just use this slope as well over there. There we go. So it's not a big deal. It's a horse apiece. So now let's do a test point. We're gonna 0, 0 does not lie on this solid line. Remember when we have the greater than or equal to or less than or equal to, when there's the equal portion to it, we make a solid line. Does not need to be perfect at all. Try to hit the dots the best you can. Not a big deal. So test point, we're going to do 0, 0. And now we can use this original standard form. Even if you got it into slope-intercept form, this standard form is really easy to use. So we're going to go 2 times 0 plus 5 times 0. Is that, question mark, greater than or equal to 10? We get 0 is greater than 10. That's false. So we were testing this point right there, this region, the origin. And this point is not a solution because it made a false statement. Therefore, everything on its side of this line is false. So what's the true side if this is the false side? This is the true side. If we get a false statement, we shade away from the line. Away from the line where the test point is. So the test point is on this side, we shade away from that.